move on. So let's start. The last lectures we were dealing with neuroevolution, and the slides are already there, and so we sort of finished the subject. Although we will see probably some examples during the rest of the semester as well, because it's an important topic. And actually, today we will touch it as well. The topic of today talk is it's an interesting topic. I will be talking about various search mechanisms and how they support diversity. Basically, that's the main topic. And among those, I will be talking about the so-called Tabu search, and then a scatter search algorithm, and finally the so-called novelty search. So you will see that sort of the underlying topic is what is diversity, how we support the exploration, and how we can make the search mechanisms more efficient. And it's interesting that these algorithms are of a very different origin. So that the Tabu search is a local search heuristics, and it originated in the 70s and 80s as a sort of improvement of hill climbing. That's how it started. So we will see the exact mechanisms of the Tabu search. Then the scatter search is sort of a global search mechanism, and it tries to make the population more diverse. The novelty search is a hot topic. It's a very modern algorithm proposed in, I think, 2017 or 18, and so it's a very modern algorithm. And the idea is that that the diversity of the population and sort of new individuals that differ very much from the previous ones are the important thing. So the diversity and novelty, as this is called, is the sort of common theme in all those algorithms. So that's the program, and let's start. I will sort of historically start with Tabu search, and then we'll move on to scatter search. Sometimes these two, Tabu and scatter, they are referred to as a sort of a combination of two algorithms that work together. It's because they were designed this way. Like the scatter search was sort of designed to be like a global search that's using the Tabu search local search procedure, but they can be seen very independently. And so all of these approaches are sort of meta heuristics, as they sometimes called, meaning that they can be tailored, they can be applied to different problem areas, and so they are variations of these algorithms. Okay, let's move on, and we'll start with the Tabu search. So the idea of Tabu search, as I said, it's quite old in terms of computer science and IT. So it's decades old, and the idea is that to make the local search more efficient, we will have a mechanism to remember the positions we were in already, and we pronounce them taboo. So you probably know the notion of taboo, right? Sometimes in English it's spelled like taboo, uh, and it's actually a Polynesian word, uh, and in Hawaii, and it's in Polynesia, Philippines, and Hawaii. In Hawaii, it's spelled kapu, and the word means something that's sacred, forbidden. You can't touch it. So in those islands, the natives usually offer some, um, well, anything like from fruits to flowers to their gods, and when they put these things on the altar, they're taboo. You can't touch them. So that's the idea of taboo, right? It's been the it's been used since the James Cook sort of discovered, in quotes, these islands to Europeans, and they've been popularized in our environment by Sigmund Freud, who used the term for something that's sort of forbidden, right? So the idea of taboo is that we will remember the visited positions, and we pronounce them taboo. How to do it? Well, uh, well, first of all, the motivation is nice, right? We are doing local search, so we're in some position, and you're deciding. Imagine the hill climbing type of scenario. So you're creating the mutations, and you're moving from here to here, and then you have the XT, you have the XT prime, and then you're comparing the fitness of the XT with the fitness of the new possible candidate, the mutated guy. And if the fitness is of the new guy is better, you're sort of taking this one, right? And then we're making another jump. If it's not better, we probably repeat the hill climbing algorithm. Now the idea of taboo is that we remember the history of our jumps, and we say, okay, these will be now these will be where's the where is it uh, these historical steps will be forbidden, and we cannot go there. So if we end up doing our random mutation that would attempt to go here, we say no, it's a taboo. And so the way how we do it is that we have some kind of taboo set or taboo list of the previously visited positions, right? So that's the main idea. The algorithm that you have in the slides is actually trying to express this on this example. So we have a simple hill climbing scenario. This you understand that the mechanism of a taboo set can be easily applied to any type of evolutionary algorithm if you know how to handle the taboo set, right? And the idea is that local search, where we're doing the mutations, is sort of careful, and we are not using the previously uh, visited positions, right? So we have to remember those. In the algorithm, the sort of simple implementation of the taboo list is that we have some kind of buffer where we put, and now the important thing is what we put there. You can either put the individuals. This is not the standard way. You are not trying to put the individuals there because the individuals can be big. So if for special problems, you, instead of individuals, you put the so-called moves there, meaning you remember the operation that took you from one position to another, and you put the move there, like the form of the mutation. So for example, if your algorithm operates on a graph or a binary individual, so if it's a binary individual, then the mutation is swapping some 0 to 1, for example. So in your buffer, you remember this position, this operation uh, that's changed. So or if you're operating on a graph, say, so the usual mutations there are sort of inserting edge in a graph, or if you're solving the TSP, so you're swapping nodes, right, of the graph. So the idea is that the buffer does not contain complete individuals, but sort of an operation how to create those individuals, some information that you can reconstruct the individual. They're called moves. Um, then uh, the list has some kind of limited length, right? So the first implementation idea can be that you have some kind of specified length of the buffer of the Tabu list, and once it's full, you're adding some guys, and once it's full, you're just start deleting the oldest guys from the list. Nevertheless, we have more uh, complex mechanisms for this, and so for the Tabu list, we have the moves, the operations, as a sort of efficient representation of the individuals, and the clever idea how to solve the limited size of the buffer is, and it's also better for the algorithm, is that we have sort of a time limit. It's called tabu tenure, and it's basically a number of iterations uh, for which the individual stays in the Tabu list. So this can be static. So you say, okay, I have some t, like, I don't know, 20 iterations, and the individual stays in the Tabu list for 20 iterations. It's a sort of a short-term memory, right? And so it will limit the search for some time, like 20 iterations, and then it disappears from the Tabu list. Sometimes it's set in a dynamic way, so usually it's some random number from some interval, like T min and T max. So that's another way, but it's just a technical issue, right? The important thing is that each individual has some time uh, to spend in the Tabu list. And based on your algorithm, your application area, you're uh, setting this to be a reasonable limit. So that's the Tabu list, and the with the Tabu tenure, sometimes so basically, if you think of it, the idea is that we sort of have a hill climbing uh, with uh, some no-go zones, right? The tabu list that tells us some no-go zones. On the other hand, um, sometimes it makes sense to make it more stochastic. So the stochastic version can resemble the annealing type of operation, which means that when you're deciding if the for example, there are lots of individuals in the buffer, and so you're in a position that you're jumping around, and all these are no-go zones. So you cannot really go anywhere, and your loop is taking too long. Then it might make sense to actually accept one of those solutions and say, okay, in this sort of simulated annealing way, you either have a probability, so you're saying, okay, I accept this solution even though it's in Tabu list for some time, and uh, just to move out of this region because I'm stuck here for too long. So this is actually called this mechanism is actually called aspiration, which means that some individuals from the uh, Tabu set can actually be selected in special cases. So we're having aspiration criteria, and these are usually based on the fitness. So maybe if the new solution is uh, much better than current, or another thing might be uh, that's sort of the simulated annealing approach, that if you're stuck for some time, you sort of lower the tenure of the individuals in the buffer, right? So the idea is that if we're in a position xt, we're moving somewhere, this is xt prime, and this is in Tabu list, so we should not be accepting this. But for case that the fitness of this guy is much better than the original one, and we're sort of getting stuck here for some time, so we're taking this one anyways, and then continuing from here because this looked like a sort of a dead end, right? Um, so that's the aspiration criteria, one mechanism that sort of makes it more stochastic, and it's another mechanism how to avoid stuck in local optima. And we have one more mechanism, and that's pretty much it. And the another mechanism is that it's called frequency memory. And the frequency memory is actually that for each of the instances we have, or we remember how many times it's been visited, right? It has been visited. And so the more times it has been visited, the less chance it should have to actually be selected, right? So the frequency memory is just a mechanism how to remember the frequency of visits for the possible individuals, for the instances, and then it can be used to actually improve the search. So one of the possibilities is that we're visiting, if you're selecting where to go, you prefer the ones that are that have low frequency, right? Visiting the low frequency ones. So we are visiting the low frequency ones, which usually means that you have the fitness, and then you also have the frequency memory, such as pi, and so you're somehow multiplying this by uh, something like 1 over pi, or some other operation. So you're biasing the fitness by the frequency in order to support the low frequency ones, right? That's one possibility how to do it. So you see that this is another of those like diversification mechanisms, right? Some solutions that were visited quite often have much lower chance to be visited again, right, by the frequency memory. Another approach that they actually found quite useful was that we actually restart the search. So we're somewhere, we're sort of stuck, and then we're saying, okay, so let's restart the search from some position that's infrequent. So we're searching here, find some low frequent position, move there, and start the search from there. Right? So this is a restart from low frequency. That's another mechanism. It's called restart diversification. So that's pretty much it for the. Let's summarize it somehow. Uh, we have a search that's generally local search. I'll change color. So Tabu is a local search, and the idea is that we have a set of visited positions, usually represented as set of visited moves or actions, uh, and we are trying to avoid this. The, the Tabu list has some additional mechanisms, so it works efficiently, that were added to the very basic algorithm. One is that we have the so-called tenure, the time the solutions can spend in the Tabu list. And by controlling the tenure, we're sort of creating the memory to be more short term or longer term. Uh, then we have the mechanism that's called aspiration. That basically means that we can actually accept the solution from a Tabu list if it's really good or if we're stuck in a local optima. And for the same thing, to avoid searching the areas where we already been to, is the frequency. We're remembering the frequencies. So we have the frequency counter for each of possible positions and or solutions, and selecting, we're preferring the ones that were visited less often, right? And the preference can be that you're creating a compound fitness, uh, or that you're restarting the search from one of the low frequency positions. So this is the mechanism. Uh, it's been used in practice in many actually successful applications. So uh, it can be formulated like discrete domain optimization. And probably more often, it's used in discrete domains like traveling salesman problem, vehicle routing, and similar. Uh, some applications in DNA sequencing and those like difficult practical uh, combinatorial optimization problems. It can also be formulated in continuous domains where the individuals represent vectors of floating points. Then sometimes the taboo list is not actually uh, considered to be a list of exact solutions, but it can be uh, some kind of rules or constraints telling us, for example, that in the Euclidean space, like for example, this area is no good, so don't go there, right? So the representation of a taboo set for floating point domains can be different than just a list of concrete solutions. It can be constraints on the areas, it can be constraints on the directions, and so on. You can also think of the positive feedback from the taboo list. Sometimes it's called like a long-term memory. So you remember where you were, and the algorithm can sort of identify regions that were not visited or not that often. So it can tell you like focus your mutations in this direction because we haven't explored this part yet, right? So yeah, that's pretty much it. You have an example for sort of a very simple hill climbing like algorithm for solving a traveling salesman problem, uh, where the taboo list is uh, as sort of a good list of good positions, and but that's just one of the possibilities. So yeah, taboo search actually quite efficient. Uh, it really, when implemented well, especially for discrete domains, it is a good mechanism to avoid local optima during your local search. You can avoid cycles and sort of repeating solutions, right? So it definitely supports exploration. Uh, there are some cons. It takes time. Uh, it Because it increases number of iterations, right? If the taboo list should like work well, so it can constrain the the solutions you're considering. So maybe you're doing your hill climbing, I don't know, 100 times. And also, as you see, the evolution of the algorithm from the simple list that was not that efficient, incorporating the tenure mechanism where you're setting your time limit, then the aspiration or the frequency computing and sort of biasing. So you can imagine that you have some parameters that should be tuned. Uh, so sometimes for the algorithm in the most sophisticated version, you have to do some hyperparameter search. You have to tune the parameters, have some knowledge about it. So that might be also a negative thing. But in general, Tabu search, quite an efficient local search. And now you understand that it's sort of meta heuristics, that it can take some other heuristics like your mutation in your genetic algorithm, the hill climbing mutation type of thing, and just adding the mechanisms of the memory and avoiding going back to already visited solutions, basically, right? So that's the idea of a taboo search. I hope that's clear. I like it. It's sort of a simple but working efficiently. And now we'll focus on the second algorithm in our list, and it's called the scatter search. As I've said, scatter search is a global algorithm. It also has a long history. Uh, it actually started in the field of optimization in mathematics, where they were proposing so this started in constraint optimization. So they were trying to optimize some function with respect to several constraints that were basically conditions on the some additional conditions on the function, saying like the variables cannot go to this direction, cannot be in this area, and so on and so on. Constraint like that. And one of the meta algorithms that developed in this is you're trying to relax some of the constraints and to support the search. So that was the origins in the 70s. But the algorithm now evolved in a so in the evolutionary type of algorithm. So the idea is that it's really a global search that tries to support exploration. And the idea how the exploration is supported is that you're focusing on diversity of new solutions. So you're generating the new solution to be as diverse as possible. And the way how you control the diversity is that you're keeping a special set of solutions that you're using in creating the new solutions, and this is called a reference set. So we will be talking about a reference set and the set of solutions selected in a special way, and we will see how this reference set is used to support the diversity. So the scatter search, as I said, is a global search. So basically, we can think of it as sort of a global, the outer loop of the evolutionary algorithm. So you have a population, and you're creating a new population. And so this is population T, this is population T plus 1. And you're selecting your reference set that helps you to create the more diverse population. But here, by going from here to here, this is the scatter search. This is the scatter part. But you need some local search operations. These can be mutations, hill climbing like algorithms, or even the Tabu search. So that's why sometimes they are sort of considered to be like a pair, because the scatter search is a convenient sort of outer loop taking care of the population, but calling some local search algorithms such as Tabu or other in order to actually locally modify your individuals here and then going to next population. And so this is the Tabu can be part of scatter search where the local search is necessary, but you can have hill climbing as well or other local search heuristics there. So the scatter search, as I've said, proposed for solving hard optimization problems, and now we will see some generic loop how to do it, and we describe the parts of the scatter search. So on a general level, I will try to describe it now from the evolutionary scatter search as EVA point of view. So you're basically generating the initial population, P0. You're keeping always the reference set. We will be discussing the mechanisms how to update it. But the reference set is basically, for the beginning, it's the subset of the initial population, P0. And now we have a cycle, right? We like it. So basically what we're doing is that we're creating the P1 population by arithmetic crossover of the guys at the reference set. And then we apply local changes on the P1. So here we have the mutation, can be hill climbing, can be the Tabu even. So we're applying local changes to the individuals of the new population that was created by using arithmetic crossover or some kind of crossover. The crossover is important, of the reference set, right? That's the important thing. And then we have the mechanism that we're updating the R1 from the R0 by using some members of P1. So the idea is that we basically have those phases. We're initializing the initial population. We're initializing the reference set by a selected subset of the initial population. And then the new population, PT, is created by a crossover operator from the previous reference set. Then we apply local changes on PT, meaning mutations or similar local searches on individuals. And then we're updating the RT from RT plus 1 and PT. So the reference set is updated by some of the new members of the new population, right? So we're using crossover here. While we're crossing over only the guys from the reference point, we're using mutations or some kind of local search after the crossovers. And we are updating the set of reference point here. So this is the idea how the scatter search works as a special form of evolutionary algorithm. You see, we have a population cycle. The only difference is yes, yes. I see the one moment. Yes, Martin. Yes. Yeah. The population, that's sort of like in evolutionary algorithms, right? We in evolutionary in evolutionary strategies, where you can have the sort of booming the number of individuals, where you do your candidates and then you squeeze it again for the size of a population. So this is this sort of a similar approach as here. Yeah. So now I will try to reformulate this, because if you happen to read any kind of paper uh, on the scatter search, they have slightly different vocabulary. So the same algorithm that I just described, I will try to do it again, but using the names they're using in scatter search. So basically, the initialization, they call it a diversification. So diversification means that they are trying to initialize, already the initialization is done, so the members of the initial population are diverse. Right? Then they also use the so-called improvement on P0, and the improvement is the mutations, the local search. So this is the initialization, but a special one. This is the local search, the mutations. So you see that you start with creating, initializing, and then already mutating. Then they have the reference update, the reference set update. We will be talking about this in detail, the reference update. And this is the beginning of the loop. Now we're looping, and so we're generating a subset from the reference points. We're combining them, and then doing improvement again. And so basically, we're using the reference set to generate the individuals. Usually what we're doing is we're generating pairs at random, or we're generating pairs of those reference set. The combination is a crossover. And the improvement is, again, the mutations, right? Then what we're doing, we're doing reference update. And so this is the basic idea of the loop. And so what you see is that you have the population here. You have the population here. You're initializing the population. You're doing local search on the population, and then you're doing the update of the reference points. So here we're talking about the reference. Then we're using the reference only for creating the pairs and crossing them over. So we're creating the pairs, crossing them over, mutate them, and now at this point we have the PT, right? So the PT is created by this. Then we use the PT and the R T minus 1, that's this one, right? To create a new RT. And we're going back, right? So the population is there, but as Michal mentioned, we have the initial population we're working on, and then we're sort of creating from the reference set, we're creating the new population, but the new population then exists only for a while here, and we're updating the reference set and then going back with the new reference set and creating again, right? So the population can be seen as sort of a list of candidates, and we're selecting the candidates, uh, the new candidates, the suitable candidates. But what is kept between the generation is the set of reference points. Right? So to summarize the operations, because we have some new terms, so don't get confused, right? They call diversification, which is like a smart uh, initialization. They called improvement, what is basically local search, mutations. Uh, the combination, the combination is actually crossovers. Uh, the subset generation. So you're taking the set of reference points, and now you want to create uh, your new candidates, right? New population for a while. So what they're doing is that they something like a selection. This is sort of a parental selection, but this is usually deterministic. So what they do is they take all the pairs, they just generate pairs of the reference set. Then they do so the subset generation can be seen as a parental selection, but the selection is sort of everybody with everybody, right? Uh, then you have the crossovers. Then you have the mutations. Crossovers are called combinations. Mutations are called improvements. And then you're updating the reference set, and we will actually talk more about the reference set update, because that's the key thing, right? But otherwise, you see that we have the elements we've already seen, and what is different is that the complete population is not surviving from one generation to another, but it's rather the set of reference points that is surviving, right? Yeah. So, how to do what to do with the reference set? How to actually do it? Well, the idea for the reference set, because the reference set is important, right? It's the only thing that survives between generations. So that should carry the information, the key information, the best individuals from the previous population. And the main point of the scatter search is that it should be a blend of the fittest individuals and the diverse individuals. So the idea is that the reference set uh, is a, created with a combination of good fitness and diversity. So good fitness and diversity. So the diversity, good fitness, of course, you compute the fitness and that's it. And the diversity, you're basically looking at your solutions, and you're computing some kind of distance of the individuals. If it's points in Euclidean space, so if these are vectors of reals, then this can be a Euclidean distance, right? If you have binary vectors, you have some kind of Hamming distance, and so on, right? So for the diversity, you compute the distance of the individuals. And when building the reference set, you're trying to somehow uh, maintain those two criteria, to have the high fitness guys there, and to have the guys that are diverse, not similar to other members of the reference set, right? So basically, what you're trying to do, that you're trying to maximize the so when you're adding some guy to the reference set, uh, you're you're what you're trying to do is that you're computing the distances from the guys in the reference set, and so you the distance of the x from all the reference set is usually considered to be the minimum, right, of the distances of x and y, and this you are trying to maximize. So you want this guy, basically you want this guy to be farther away from the guys already in the references. So this one will be better than this one, right? So we're computing the distance of the candidate to go to a reference set, and we're trying to find the candidates that are far away from the existing reference set members, right? So that's the diversity. And the high fitness is the high fitness. So we want to actually combine these two things together. Even the initialization that's that's called diversification here is usually this combination of using the diversity and fitness. So even during the initialization, the idea is not to start with random guys, but to uh, try to create diverse enough random guys. Okay, so the this is how the general principle, what how to update, how to initialize and update the reference set, but there can be different mechanisms how to do it, and so during there are several versions of the scatter search algorithm. Uh, the reference set can be updated either in a sort of slow way, incrementally. So each generation, we're adding one or two new individuals into the reference set, or it can be completely renewed in every population. Um, and so we can have different mechanisms how to update the the reference set, and they have been tested. There's no clear winner of how fast to do it. Uh, so uh, if we try to wrap it up, the scatter search is a cool evolutionary algorithm. It's a global heuristics, and it's been designed explicitly to operate on diverse individuals, right? The key point is there that we have a diverse population. So we're computing a distances in the genotypes here, and when we're generating new ones or considering which ones will go into the reference set, uh, the diversity is an important criteria. So it definitely has exploration capabilities because it explicitly works with the exploration. And mm, this algorithm is actually implemented in even in commercial systems. So there's a software called OptQuest, and it's a commercial successful black box optimizer uh, that is especially focused on problems where the objective function, the fitness, is really expensive, takes a long time, so the number of evaluations is sort of limited. And so the scatter search ideas are actually used in practice to solve successfully hard optimization problems. Because the if the problem is hard, you have a higher chance to stuck in local optima, and that's why these mechanisms to support exploration uh, can be very useful. And as we could see, this can be combined with diverse local search uh, operations, and they can be mutations, or they can be hill climbing, or it can be the Tabu search we were talking about before, right? So they all fall into this improvement procedure that's working on individual levels and performing some kind of local search. Perfect. So that's sort of a wrap up of the scatter search. They started digging here. Is it okay, or is it too noisy? Please write me in chat if it's okay. If not, I'll be moving to my bathroom. It's okay so far. Yeah. If it's too much, let me know. Thank you, Michal. Uh, Perfect. So now the last part of today's talk is about the novelty search. So the novelty search is actually it's 2011 is the 2011 is the important paper in Evolutionary Computing Journal, and it's by Lehman and Stanley. So the Stanley name should ring the bell. He's one of the guy behind the NEAT algorithm. So the NEAT algorithm was developed by Stanley when he was studying under the supervision of Mikulainen, and both these names, Stanley and Mikulainen, are now sort of active researchers in the areas of neuroevolution, deep networks, and so on and so on. So Lehman and Stanley introduced the novelty search, and it's actually uh, a long way from the 80s when people were starting to discuss the properties of the fitness function and what is a difficult problem for genetic algorithms. And again, the idea is that we should search for, we should explore basically. We should explore. Especially for difficult problems, the exploration is really important. So we've seen that the scatter search was addressing this issue already. And the Tabu search is a local procedure that is trying to do pretty much the same thing, but on a micro level, on the level of local changes. The novelty search is another attempt to do pretty much the same thing, but novelty search is doing it in a very radical way. So we will see that novelty search is surprisingly different, and I will not tell you spoil all the details now, but I try to start with some historical introduction. So there was an research in genetic algorithm that started by Goldberg in 80s, and we've heard about Goldberg as one of the authors of actually the first sort of a general textbook monograph on genetic algorithms from 89, and they observed and he was probably the first one to express it in a paper. They observed that the building block hypothesis has a problem. So the idea was that we have schemata, right? And we have a short, compact, high fitness schemata. And then we try to combine those. And by combining those schemata, we hope that we get more fit individuals. So combining those small building blocks, we're getting larger building blocks, and they're better, right? Because this solves half of the problem. This solves like some part of the problem. This solves some part of the problem. So when we're combining them, the this has some fitness, this has some fitness, and when we recombine them, we should get much better fitness, right? That was the idea, but for some problems, this did not work. So they started to call this type of fitness a deceptive fitness. Deceptive meaning like misleading, right? Uh, and the idea was that we are sort of evolving our individuals, and we want the trajectory from the original individual to be sort of smooth, and all of a sudden, ta-da, and we've reached the global optima. The deceptive function is not like that. It's leading us somewhere. We're stuck in local optima, and in order to get here, we have to start somewhere totally else. So there is not like a clear path, smooth path from the initial individual, and then sort of improving by combining those partial solutions, improving, and then reaching the global fitness, right? So the idea was that, yeah, deception is an important topic, and it means that this type of a fitness function is really hard for evolutionary algorithms uh, to solve it. And so some researchers were even proposing this sort of a level of deception as a measure of when a problem is difficult for evolutionary algorithms. So remember the phenomena like hitchhiking and collateral fitness, uh, when those blocks are sort of correlated to each other or subsets of each other, and they have different fitness. These are exactly the examples of a sort of bad deceptive uh, fitness function. And so one of the mechanisms for uh, tackling this problem is that actually you have to uh, explore. What does it mean? You have to explore more. How can you explore? When one possibility how to explore is basically to say we are doing more crossover, we are doing higher mutation rates, more aggressive mutations, and these are, in a sense, sort of a blind operators. But anyways, the exploration is actually good because you're not stuck in here. You're sort of exploring the area, and then you happen to continue and reach the higher fitness area. But the type of exploration can be different, and so the notion of novelty uh, appeared first in evolutionary robotics when people were actually solving problems from evolutionary robotics. Eva Rob, were you using evolutionary algorithms to train controllers for physical robots, and they're solving different tasks. So one of the things is when you have a robot in a maze, and for example, you want to reach this area, and the robot has some kind of radio receiver. So the robot receives a signal, and so he's trying to get into this beacon, sort of a home base or something. But imagine the scenario where you build a wall here. Like this is a very oversimplified, but nevertheless it makes some kind of sense. So you have an algorithm that is basically trying to find a path to this optimum, reaching the beacon, but all of a sudden there's the wall, right? So if you have a that's a basically constraint, and if you're trying to improve the fitness, so the fitness you can imagine is the distance towards the beacon, right? So when you're here you have a lower fitness, when you're here you have a higher fitness, but the fitness based search of the algorithm leads to the solution that you hit the wall, and then sort of every move would mean well, imagine the wall is like this or even more complex. So every move would mean that you're worsening your fitness, right? Moving here, moving here. So you don't have much uh, motivation in the evolutionary algorithm to actually go here, worsening your fitness, and then find the way, right? So that's the exploration capability, right? And the evolutionary robotics uh, says, well, first of all, we have to look at the behavior and try to search for the novelty of behavior. So while the scatter search was also concerned with the difference of the individuals, it was observing the difference by computing the distance of their genomes, right? Of their of the way how they are encoded in the algorithm. The idea from the evolutionary robotics is that it's probably not the most important thing because the individual has a very special encoding. For example, it's an encoded neural network. But what is important that you should search for different behaviors. So basically, the behavior is important. So probably you have to actually run the simulation and see what the robots are doing. And if some robot is doing something really different, then it's probably good because you're really exploring, but in the behaviors, right? So the basic idea is that you want to explore, but you want to explore the phenotypes, the way what the phenotypes are doing. So you're searching for different uh, novel behaviors, right? Not necessarily the genes, right? And so uh, Lehman and Stanley formalized this uh, and created uh, the notion of behavior space, saying, okay, so let us create somehow the space of the behaviors. So each of the behavior of the robot, of the agent, of the individual is then a point in a space. So you have to formalize this somehow, right? How to create the space, but then each of the of the individuals can be represented by a point in this behavior space. So we're talking about phenotypes. Uh, Usually, if we're talking about agents or robots, we're talking about their behavior in the simulation. Okay, so we're in behavior space. Now we will do the same what the scatter search people did. We are defining, we want to say, well, the new solution, is it original, is it novel or not? Well, if the new solution is in sort of a area like this, it's probably not very original, right? If the new solution is here, where you have only one guy here, and the rest here in this cloud, so then this one is novel. Right? It's original because why? Because it's far away from uh, lots of other individuals, right? But the individual is represented by the behavior. So this is important, right? We're not talking about the distance of vectors of the encoded individuals. We're talking about the behavior of a robot in a maze, for example. Nevertheless, the notion of distance is pretty much the same. So you defined a matrix, a distance of two behaviors, and then, okay, uh, you, you define some kind of coefficient saying how uh, how dense is my neighborhood or how sparse is my neighborhood, right? So you defined sparseness. So the sparse is the opposite of dense, right? So you define some kind of sparseness, and how do we do it? Well, for the guy X, the sparseness is a uh, sum of distances of some of its neighbors, right? So you're summing the distance from, say, uh, k nearest neighbors. So you're selecting uh, k individuals that are closest to this guy, and you compute the distance, and you sum it, multiplied by k, and that's the number that tells you how far you are from everybody. Well, not everybody, only k nearest neighbors, but that's a good indicator. So that's the sparseness coefficient. The larger the number, right? The more sparse area I'm in, uh, and so this is the number that can be used by the algorithm to identify what solutions are uh, new in behavior sense in this behavior space, right? So we're saying this is the original novel behavior. These guys are behaving pretty much the same. This is the novel one. So how do we compute, how do we use this sparseness in the algorithm? So the algorithm of novelty search is actually pretty easy. Uh, we already know the scatter search and everything. The main idea you should remember is that we are concerning the distances in the behavior space, right? So the algorithm, how the novelty search works, novelty search. So the idea is that we will have an archive of novel individuals. And the novel individuals, meaning that we put into the archive only individuals where the sparseness coefficient that we computed in the behavior space is higher than some kind of threshold. So we have some meaning that if you have your individuals like this, and you're saying, okay, in order to be in archive, you should be, pretty far away from the guys. Like this can go there, this can probably go there, but not this one, right? So so you should be the sparse area of the behavior space to go into the archive. So we're computing your sparseness, and we have some threshold set, and the sparseness have to be larger above this threshold. Then you can enter the archive. And there's one more thing, that you have the archive that's global, and that that should represent, sort of a sparse individuals that you already have. And the next thing is that when you actually in the loop of your search algorithm, uh, you put what you compare the new solution, the new individual you're creating by some kind of mutation, uh, should be sparse, should maximize the sparseness with respect to the archive and the current population. So this is important to understand. So you have a global archive that you keep the so-called novel, very different individuals, right? And then when you're doing your population search, so you have some kind of population and you have the archive, and by some mutation you're creating a new guy, and you're saying, is this guy B in the, so you have a population T and the archive, and you're saying, so we have a new guy created, uh, X, and will X go into PT plus 1. And the important thing is that you compute the sort of a distance of this guy from the PT and the archive, and this has to be larger. So we're using the raw, the sparsity coefficient, and this has to be, we're trying to maximize this. So this has to be big. So when creating a new individual, we're computing the distance with respect to the current population, but also with respect to the archive of solutions. And now, I mean, notice this. This looks like the same principle as the scatter search, but the important thing is the archive does not use fitness. It uses only the sparseness, right? No fitness there. Here, we also use a sparseness, no fitness there. So the idea of the algorithm is that we are totally avoiding computing of a fitness, and the notion of the sparseness or the novelty of the individuals is the objective. Wow. So that's the main message, and that's the revolutionary thing in novelty search, where they say, no, this deserves novelty is the new fitness. So this is the most important message of the novelty algorithm, maybe of today's lecture even. We've seen the previous approaches were trying to balance the notion of novelty expressed by the similarity of individuals and codings with the fitness, and saying, okay, in our algorithm, we have to balance. It's not only fitness guided search, but we have to support the exploration and the existence of different individuals that are exploring different parts of the search space. The novelty search uh, came uh, two steps further. One steps saying, well, it's not the encoding of the individual that's important, but we should consider the behavior and create an abstract behavior space and observe the distances between individuals in this behavior space, such as how the robot performs in a maze, right? That's one thing. And another thing is that uh, we can actually leave the fitness out of the equation completely by focusing on the diversity, on the so-called novelty. We are getting good solutions in terms of fitness sort of automatically, even though the fitness is not there. So that's sort of surprising, I think. Uh, well, and surprisingly enough, when they tried it on some problems like robot in a maze or reinforcement learning, where they were training the bipeds to walk some distance, they achieved sort of state-of-the-art results without the fitness, just focusing on the novelty. There are some arguments from the reinforcement learning area that this problem is actually very difficult. So the exploration capabilities are really needed and they have to be emphasized. Some arguments from the learning algorithm itself saying it's not a random search. It is a search guided by an objective function, but the objective function is not fitness. It's the novelty. And some support from the mother nature, I would say. In natural evolution, we seldom have clear trajectories that we understand as sort of a smooth transition from one uh, animal into another animal, leading to successfully solving the solution. What we see is jumps, unusual things, complex things appearing, and so there's no like incremental evolution that can be traced visibly, but sometimes there are jumps, and so probably the aspect of a novelty and originally of some solution is important, uh, and for problems that are hard, maybe with the deceiving functions where the function does not lead us naturally by combining sub-solutions into a new solution. Maybe this novelty as sort of coming with a surprise solution, exploring part of the search space that we did not explore, and maybe if it were not for the novelty, we would not have come there into this area because the fitness function would lead us only to certain areas. So this aspect of novelty is seems to be really important. So that's it for the for today's talk. The novelty search, I think, is surprising, but if you see it in the light of evolution of scatter search, tabu search, and deceiving functions, it's not that surprising. So thanks a lot for your attention. That's it for today, and see you next week.